Hi guys, this is the EdExcel Further Maths Decision 1 paper from the sample papers. Okay, so let's just get straight into it. Question 1. A list of n numbers needs to be sorted into descending order starting at the left hand end of the list, and for part A we have to describe how to carry out the first pass of a bubble sort on the numbers in the list. Well, we've got this following explanation. In the first pass, we compare the first value with the second value and swap these values if the second is larger than the first. Okay. We then compare the value, which is now second, with the third value and swap if the third is larger than the second, and we continue in this way until we reach the end of the list. And now for part B. Bubble sort is a quadratic order algorithm. A computer takes approximately 0.021 seconds to apply a bubble sort to a list of 2000 numbers, and we have to estimate the time it would take to the computer to apply a bubble sort to a list of 50,000 numbers. Make your method clear. Well, we know that it takes 0.021 seconds to sort 2000 numbers, and we first of all for part B need to work out our sort of scale factor. That would simply be 50,000 divided by 2000. Okay, and then we square this, because if you go back to the question, we were told we have a quadratic order algorithm, and then we multiply this value by 0.021. So the time is equal to 0.021 multiplied by 50,000 over 20,000 squared. And if we work this out, so let's just grab our calculator. We have 0.021 multiplied by 50,000 over 2000. Then we square that value, we get a value of 13.125. So we have 13.125, and I recommend writing down the units for consistency. So we have 13.125 seconds. Question 2. For part A, we have to define what is meant by a planar graph. And we've got the following explanation. A planar graph is a graph that can be drawn so that no arc meets another arc except at a vertex. And now for part B, starting at A, we have to find a Hamiltonian cycle for the graph in figure 1. Of course, a Hamiltonian cycle, that's one in which we have a cycle that includes every vertex. Okay. Now for part B, when we come to find out that Hamiltonian cycle, if we start at the point A, we can go A to B, B to C, C to D, D to E, and then we can go from E to G, and then we can go G to F, and then F to A. So if we write that down, we have A, B, C, D, E, G, F, A. Okay, so this over here is our Hamiltonian cycle. And now for part C, arc AG over here is added to figure 1 to create the graph as shown in figure 2. And taking A, B, C, D, E, F, G, A as the Hamiltonian cycle, we have to use the planar algorithm to determine whether the graph shown in figure 2 is planar, and you must show your working clear. You must make your working clear and justify your answer. Okay. So part C we'll do over here. The first thing we do with these sorts of problems is we've got our Hamiltonian cycle A, B, C, D, E, F, G, A. Okay. And then our next step is to list the edges inside this cycle. So we have AF, then we have AE, and we have AD, and then we have BG, and then we have BD, and then we have CG, and then we have CE, and then if we take a look at the point D, we've already done BD, we've already done AD. If we look at the point E, EC we've already done, EA we've already done, so we're left with EG. Okay. So what you can see over here, we have 8 edges listed which are inside this Hamiltonian cycle. Okay. So once we've done that, we draw a line over here, like so, and then you can pick any edge. For example, if we pick AF, we write down the letter I. Okay, so if we take a look at AF, let's draw a red line through it, like so. And you look at the edges which intersect AF, those are BG, CG and EG, and then we write down the letter opposite to I, which is O, for those. So you'll notice also BG, CG and EG do not intersect each other. So we have BG over here. Let's just shade this in a different color. We have BG over here, and then we have CG over here, and then we have also going through AF we've got GE. Okay, so we just draw a line through it like so. So in terms of what goes through the red line, we've got the 3 blue lines, so we put the letter opposite to the I for those edges. So we have BG, we'll put an O there. We've got a CG, we'll put an O over here, and we've got an EG, we'll put an O over here, and then rule off like so. And then we look at these edges and we look at what crosses through them. So if we consider the edge BG, we'll do this in green. So if we consider BG over here, let's draw it straight. So considering BG, like so, what crosses BG, if I draw this in a different colour, we've got AF, which has already been crossed off, and then we've got AE, so we've got AE over here, and we've also got AD over here. Okay, so we've got AE, we'll put an I over here, and we've also got AD. We'll put an I over here as well. So that's BG. Let's now consider CG. So if we go back to the green and consider the CG is over here. What crosses that would be the AF, the AE and the AD, and also we've got this BD crossing it as well. We've got BD which crosses over here. Okay, so we go back over here, we look for BD, we put an I over here. So that's CG done. Let's now look at EG. So let's go back to the green pen. So EG, that's over here. And we take a look at what crosses that. That's only the AF, which has already been crossed off. Okay. Now we take a look at the letters over here. So let's just rule off over here. If we consider the AE over here, what crosses it is the BG and the CG, which we've already crossed off. We now consider the AD. What crosses AD is just, if we consider AD, I'll grab a different colour. If we consider this AD over here, let's draw a line through it. What crosses it is just this EC over here. Okay, so we put an O where we have EC, and then we see over here everything is labelled, and because during the crossing phase of this problem, because when we crossed the lines they never intersected each other, we can therefore conclude over here that we have a planar graph. And in terms of what this looks like, let's draw out this graph again. So we have A, B, C, D, E, F and G. E, F and G, and then obviously G goes back to A. Everything inside, we have AF, which is inside, so if we grab a different colour, AF is inside. Also inside we have AE, that's over here. We also have AD, that's over here. And we also have BD, that's over here. So that's everything inside. We'll just tick those off over here. And everything outside we'll do in a different colour, like this colour. So outside we have BG, so let's join those together. So that's BG. Then we have CG, so it's joining C to G, that's over there, and that's that done. And then we have EG, so starting at E finishing at G, that's over here. And then we have CE. CE is over there like that. So this is our completed graph in a plane. Okay, you'll see that the lines don't intersect each other. Okay, and that's consistent with our definition of a planar graph over here. So what we have drawn over here is a planar graph. Question 3. For part A, we have to explain clearly the difference between the classical travelling salesperson problem and the practical travelling salesperson problem. And we've got these definitions over here. in the case of the practical problem, each vertex must be visited at least once, and in the case of the classical problem, each vertex must be visited just once. So I think the key difference over here is the wording. With the practical, it's at least once. With the classical, it's just once. Now for part B, we've got this table over here which shows the least distances in kilometers by road between 7 towns A, B, C, D, E, F and G. The least distance between B and G is X kilometers, where X is greater than 25. Pretty needs to visit each town at least once, starting and finishing at A. She wishes to minimize the total distance she travels, and by deleting B and all of its arcs, we have to find a lower bound for Pretty's route. So if we take a look at our table over here for part B, the first thing we were instructed to do was to delete B. Okay? So if we go ahead and delete B, remember we also have to delete vertically. Now it doesn't matter which vertex you start at. For example, if I start at A, we'll label A with a number 1 and then we'll delete all of A, like so. Okay? And if you look down A, looking at the smallest number, that's D. So we begin over here with AD, which has length 16. So then we delete D, like so, and then we label D with a number 2. We now look down both A and D and look for the smallest number. You'd find the smallest number to be F, the 18 over here, which corresponds to AF. So we have AF corresponding to 18. We delete the F, like so, and then we label with the number 3 for this F. We now look down A, D and F and look for the smallest number. You'd find the smallest number to be 21 over here. So we circle this 21. That corresponds to AE. And then we delete this entire row, like so. And then we assign the number 4 to the letter E. We now look down A, D, E and F. The smallest number is this 20 over here. This 20 corresponds to CE. So we delete all of C. And then we label C with the number 5. Okay? And then we look down A, C, D, E and F and look for the smallest number. You'd find that to be 32. So we delete G, like so. and then we assign the number 6 to G. So we have CG with 32. And then we add on the two smallest lengths from the arc, from the vertex we started at, which was B. So the two smallest ones, you'd find those to be 17, which corresponds to BA. And then we have 25 as well, which corresponds to BD. And if we add all these together, you'd therefore find the lower bound to equal 16 plus 18 plus 21 plus 20 plus 32. And then we add on this 17 and this 25. You'd therefore find the lower bound to equal 149. Okay? Now for part C, Pretty found the nearest neighbour roots from each of A and C. Given that the sum of the lengths of these roots is 331, we have to find x, making your method clear. So the way we can approach part C is to consider the root from A and the root from C, obviously using the nearest neighbour algorithm, and then we can find x from that. So let's first of all consider the root starting at A. Okay, so of course if we start at A, we will label A with a number 1, and then we'll delete this entire row of A, and then we look down there for the smallest one. The smallest one over here is this 16. That corresponds to D, so D will label with a number 2, and then we'll delete all of the row D. Okay, so we have A going to D, that's 16, and then we look down D. The smallest one is the 19. That corresponds to F, so we'll label F with number 3 and delete this entire row. So we go from D to F and we have 19. And then we look at F. The smallest one over here corresponds to this 22. So we delete all of this row. E we will label with a number 4. So we go from F to E, that has length 22. And then we look down E. The smallest one is this, the smallest one is this 20, which corresponds to C. So we'll delete all of this, and we will label C with a number 5. Okay, so we go from E to C, that's 20. So we look down C. The smallest one is this 32. That corresponds to G. So we delete all of this row, and then we label this G with the number 6. So we go from C to G, that's got length 32. we look down G, the one that's left is this X over here, and that goes to B. Okay, and then from B, as with the nearest neighbour algorithm, we go back to A. So let's delete all this, and if we go back to A, BA, that corresponds to 17. Okay, so we have 17, and if we add these together, adding these together, you'd find we get 126 plus X. Okay, and then we have to do the same thing with C over here. So what I've done over here is I've just copied out this table, and that's so we can redo all of this time with C. So obviously we will start at C. So let's delete all of this row. And then from C, we look down C, the smallest one, that corresponds to 20, and that's E. So we label E with number 2, and then delete all of this entire row. So we have CE, that's 20. We look down E, the smallest one over here, that corresponds to this 21, of course that's A. So we have 21, and then we label A with a number 3. We now look down A, and the smallest one is a 16, and that corresponds to D. So we delete this entire row like so, and then D we label with the number 4. We look down D for the next smallest, that's this 19, and that corresponds to F. So we delete this entire row and we label F with a number 5. Okay, we look down F, the smallest one is this 31, and that corresponds to going to B. So we have 31 over here, and then we delete this entire row and we label B with the number 6. Okay, and then from B we look down the next smallest one, that would just correspond to the X, which takes us to G. Okay, and then we want to go from G back to C. So going from G back to C, before that we have to delete all of G. So C, going from G to C, that length over here, CG, that would be 32. And then we now add all these together, and so adding these together, you'd find we get 139 plus X. Okay, so hopefully all that makes sense so far. And we also know from the question, if we go back, that the total of these is 331. So we add those together. So we've got this 126 plus X, And then we've also got this 139 plus x, and this gives a total of 331. So if we simplify this equation, you'd find 2x to equal 66, and therefore you'd find x to equal 33. And now for part D, we have to write down the smallest interval that you can be confident contains the optimal length of Pretty's root. Give your answer as an inequality. Well, for this, in terms of the interval, we have the lower bound, which is less than the optimal solution, which is less than or equal to the upper bound. We now have to find the upper bound. Remember, with the nearest neighbour algorithm, we still want the smallest root, and that would correspond to this root over here, the 126 plus x. We know x to be 33, so the upper bound is equal to 126 plus 33, which is 159, and therefore the inequality, we have our lower bound, which we worked out before, to be 149, and this is less than or equal to the optimal, and this is less than or equal to 159. So hopefully that makes sense. Question 4. We've got the network in figure 3 over here, which shows the roads linking a depot, D, and 3 collection points, A, B, and C. The number on each arc represents the length in miles of the corresponding road, and the road from B to D is a one-way road as indicated by the arrow. Now, for part A, we have to explain clearly if Dijkstra's algorithm can be used to find a route from D to A. Well, if we go back over here, taking a look at our answer, of course, Dijkstra's algorithm can be applied to either a directed or undirected network. So in other words, it doesn't make a difference if this arrow is here or not. We can still apply Dijkstra's algorithm. Now for part B, the initial distance and route tables for the network are given in the answer book, and we have to use Freud's algorithm to find a table of least distances. You should show both the distance table and the route table after each iteration. So we've got here our distance table and our route table, and we're going to be finding the distance and the route tables after 4 iterations, okay? And if we take a look at this figure over here quickly, you'll notice DB, starting at D, finishing at B, there's no direct way we can get there. Hence, instead, we show an infinite sign. Whereas if you look at BD, starting at B, finishing at D, we can get there via this one-way route, and that has a length of 2. Okay, so hopefully that makes sense. Now for this question, what we can do here is start by considering this point A over here. Okay, so if we highlight all of A like so, same thing over here, highlight all of A. Essentially, whatever we've highlighted remains unchanged. So here we have this dash, 5, 11, 8, 5, 11, 8. Same thing with the route table. Here we have A, B, C, D, and over here for this column we have all A's. And where we have these dashes, that will continue as well, and the letters corresponding to those dashes will remain consistent throughout. So here we have A, B, C, D, and where we have dashes, that will not change. these dashes will always remain here, and the letters A, B, C and D will always go along the diagonal. So let's just fill these out. We've got the dashes over here, and then we have A, B, C, D, A, B, C, D for the diagonals. Okay? Now if we consider this distance table with our iterations, if we consider this element over here, this BC, we take a look at this 3 over here, and then we compare that to the corresponding highlighted part, 5 plus 11. Of course, 3 is smaller than 5 plus 11, so we have a 3 over here, and the letter corresponding to this element remains unchanged. In other words, we still have a C for our root table. And if we consider this element over here, we compare this to with 5 plus 8. 5 plus 8 is 13. 2 is smaller than that, so we write the 2 over here. The 2 remains unchanged, so the letter here remains unchanged. Let's now consider CB. We look at this 3, and then we compare this with 11 plus 5. 11 plus 5 is 16. 3 is smaller than that, so we still have a 3 over here. The letter remains unchanged as well. We still have a B over here. Let's look at this element over here. We have 4, and we compare that with 11 plus 8. 11 plus 8 is 19. 19 is greater than 4, so we write down the 4 over here. The letter remains unchanged. We still have a D over here. Looking at these elements here, we have an infinite number, and we compare that with 8 plus 5. 8 plus 5 is 13. 13 is definitely smaller than infinity, so we write 13 over here, and we circle it. And the letter over here will change to what we have over here, that is the A. We circle that to indicate we've changed the letter. And finally, looking at this element here, we compare the 4 with 8 plus 11. You'd find 19 to be greater than 4, so we write 4 over here. The letter remains unchanged. We have C over here. That's our first iteration. Okay, so our next step is to look at B. So we shade all this in, same here, and here, and here. Now, wherever we have shaded over here, those remain the same. So we have 5, 3, 13, 5, 3, 2. The letters remain unchanged. We have B, B, A. And of course, going across, those remain unchanged. So if we take a look at this element over here, this AC, we compare this 11 with 5 plus 3. 5 plus 3, you'd find that to be 8. 8 is less than 11, so we have 8 over here. We circle it because we've replaced the 11 with 8, and also the letter C will be changed to B. So here we have the letter B. And for this element AD, here we have an 8, and we compare that to 5 plus 2, which is 7. 7 is smaller than this 8, so we have 7. We circle it because we've replaced the 8. We circle it because 8 is greater than 7, and we change this letter D to this letter B, and we circle it. Looking at the element CA, we look at this 11 and we compare that with 5 plus 3, which is 8, and 8 is less than 11, so we have 8 over here, we circle it, and we replace the A over here with B, and we circle it to indicate we've changed the letters. And if we take a look at the element CD, here we have a 4, we compare that to 3 plus 2, which is 5, 4 is smaller, so here the 4 remains as it is, and therefore the D remains as it is. Looking at the element here, DA, we compare this 8 with 5 plus 13, which is 18. 8 is obviously smaller, so we have 8 over here. Okay? And the letter remains unchanged, we still have A. And then for this element, DC, we compare this 4 with 13 plus 3, which is 16. 4 is obviously smaller, so here we still have 4. And here the letter remains the same as C. Okay? And then we see that we've completed our second iteration. Let's now take a look at this letter C over here. Okay, so we will now take a look at C, and obviously those elements remain unchanged, so we have 8, 3, and then we have 4 over here, and then we have 8, 3, 4. And in terms of the letters, we have B, C, and then, so here we have a B, C, C over here, and then here we have B, B, D. So we have B, B, D. Okay? And for this element AB, we compare this 5 with 3 plus 8, which is 11. Obviously the 5 is smaller, so here we still have 5. And if we take a look at the element AD, we compare the 7 with 8 plus 4. Obviously 8 plus 4 is 12. 7 is smaller, so this element 7 remains unchanged. And in terms of the letters, those letters remain unchanged as well. Here we have B and B. Okay? And if we now take a look at BA, we compare the 5 with 8 plus 3. 8 plus 3 is 11. 5 is smaller, so we still have a 5 over here. The letter remains unchanged. We leave that as A. And we now look at BD. BD before was 2, and then we compare that with 3 plus 4, which is 7. 2 is obviously smaller, so we have 2 over here. The letter remains unchanged as D, as seen over here. Let's now take a look at DA. So DA, we look at the 8 and we compare that to 8 plus 4, which is 12. 8 is obviously smaller. We have 8 over here. The letter remains unchanged as A. And now we compare this 13 with 3 plus 4. 3 plus 4 is 7. 7 is obviously smaller than 13. So here we have a 7. And we circle it to indicate we've changed the number. And in terms of the letter, here we have an A. We replace that A with AC. And we circle it to indicate we've changed. Okay? So let's now take a look at this D column over here and this D row over here. Now again, whatever I've highlighted, that remains unchanged. So here we have 7, 2, 4, 8, 7, 4. The letters remain unchanged as well. A, C, C, B, D, D. Now if we take a look at AB before was 5, and we compare that with 7 plus 7, which is 14, 5 is smaller, so here we still have 5. The letter has remained unchanged as B. We now compare for the element AC, we compare this 8 with 7 plus 4, so we compare 8 with 11. 8 is smaller, so here we still have 8. The letter remains unchanged as B. We now look at the element BA. We compare this 5 with 8 plus 2, so we compare 5 with 10, 5 smaller, so we still have 5. The letter remains unchanged. We still have A. For the element BC, we compare this 3 with 4 plus 2, so we compare 3 with 5, 3 smaller, so we still have 3 over here. The letter still remains the same as C. For the element CA, we compare this 8 with 8 plus 4, so we compare 8 with 12, 8 smaller, so we still have this 8 over here. The letter remains unchanged as B. And finally for CB, we compare this 3 with 7 plus 4, so we compare 3 with 11, 3 smaller, so we still have a 3. The letter remains unchanged as B. We therefore see the entire matrix has not changed, and therefore, well, let's just write that down. We have no changes, and therefore we have an optimal solution. Okay, so hopefully that bit all makes sense. Now for part C, we have to explain how the final route table can be used to find the shortest route from D to B, and we have to state this route. Okay, so we want to start at D and finish at B. So let's just take a look at this table over here. We want to start at D, finish at B. Okay, perhaps if I indicate this, we want to start at D and finish at B. So what we do over here for part C is we look at this D in the 4th row, okay, and we also look at this B in the 2nd column, okay. And you'll notice the corresponding letter is a C, as shown over here. So you'll find over here that there is a C. Okay, and therefore we'd have to then go to C. Okay, so let's just write that down. So we start over here at C then. So we look at the C from the 3rd row, and we still look at this B from the 2nd column. Okay, so we look at the B from the 2nd column, and you'll notice when we compare those, indeed we have a B. So you'll see that there is a B. And therefore, in terms of the root, we have D, C, B. So hopefully the color coordination makes complete sense. Okay? Now for part D, there are items to collect at A, B and C. A van will leave D to make these collections in any order and then return to D. A minimum route is required, and we have to find the final distance table and the nearest neighbour algorithm starting at D to find a minimum route and state its length. Okay. So the first thing we need to do is, well, I think it would help if over here we take a look at this final route over here. Sorry, this final table over here. Okay. So I've just copied out those tables from here just to give myself a bit more room. And if you go back to the question somewhere, it says something about starting at D and finishing at D. And we have to use the nearest neighbour algorithm. So if we take a look back over here, if we start at D, alright, we'll label this with a number 1. Now perhaps I need to move all this down a bit. So we start over here, and then we delete all of this row, and then we look for the smallest letter. You'd find, the smallest number. The smallest number, you'd find that to be 2, which corresponds to B. Okay? So we have D, B. So B goes, number 2 corresponds to B. So then we cross out this entire row over here. And then we look down B, the smallest is 3, which corresponds to C. So we put a number 3 over here, and then we cross out C over here. And then we look down C, 8's left over, and that takes us to A. And you'd find, therefore we have this 4, which corresponds to A. And then we want to go back to D. And going back to D, this is our route which we wish to take. And then we have to look at this table over here. Now, if we take a look first of all at DB, DB, we know from part C of the question, to go from D to B, we have to go DCB. Okay? So we have D, C, B. And then we still have remaining C, A, D. Now, if you think about it, if we go from B to C, well, let's think about it from scratch. We start at D, we go to C, then we go to B, and then from B we go to C to go to A. And if you go back over here, does that make sense to do that? So what I'm saying so far is we start at D, we go to C, and then C we go to B, and then what I'm suggesting is we go back to C to go back to A. That's quite long. So instead, whilst we're at B over here, we can go directly to A. So hopefully that makes sense as to why we don't go back to C from B, because that route will be 3 plus 11. Instead we can just go straight to A directly, and that has a length 5. So instead what we can have is D, C, B, and then we can go straight to A and then to D. Now we know DCB, that's correct. Now let's look at BA. If we take a look at BA, that's definitely correct. So starting at B, finishing at A, that gives A as shown over here. So this bit is correct. Okay, so we have D, C, B, A. And then we're at A and we want to go to D. Now if you think about it, we're at A already and we want to go to D. But the way we can do that is we'll have to stop off at B first. So we go from A to B. Okay, as seen over here. And then once we're at B, if I grab myself a different colour, once we're at B over here, we wish to go back to D. So we're at B, we wish to then go back to D, and we still have this. The way we can do that is go to D directly. Okay, so this over here is our root, so hopefully that makes sense. So that's our root. So this over here is our root. And in terms of the length, well, DC, starting at D, finishing at C, well, if I grab a different colour, well, starting at D, finishing at C, you'd find that to be 4. So DC equals 4. And then C to B, starting at C, finishing at B, that's 3. And then B to A, starting at B, finishing at A, that's 5. And then starting at A, finishing at B, so starting at A, finishing at B, that's 5. And then starting at B, finishing at D, so start at B, finish at D, that's 2. And if we add all these together, you'd find we get 19, and therefore we have 19 miles. Okay, and now for part E, if we take a look at part E. Now, Floyd's algorithm and Dijkstra's algorithm are applied to a network. Each will find the shortest distance between vertices of the network, and we have to describe how the results of these algorithms differ. And it's a fairly standard explanation in that Dijkstra's algorithm finds the shortest distances from one vertex to all others. So I think that's worth highlighting. We're going from one vertex to all others. Whereas Floyd's algorithm, that finds the shortest distance between every pair of vertices. Okay, so that's the end of question 4. Question 5. A garden centre makes hanging baskets to sell to its customers. 3 types of hanging basket are made: sunshine, drama and peaceful. The plants used are categorized as impact, flowering or trailing. Each sunshine basket contains 2 impact plants, 4 flowering plants and 3 trailing plants. Each drama basket contains 3 impact plants, 2 flowering plants and 4 trailing plants. Each peaceful basket contains 1 impact plant, 3 flowering plants and 2 trailing plants. The garden centre can use at most 80 impact plants, at most 140 flowering plants and at most 96 trailing plants each day. The profit on each the profit on Sunshine, Drama and Peaceful baskets are £12, £20 and £16 respectively. The garden centre wishes to maximise its profit, and we have to let X, Y and Z be the number of Sunshine, Drama and Peaceful baskets respectively produced each day. For part A, we have to formulate this situation as a linear programming problem, giving a constraints as inequalities. Well, I think it would help if we put everything into a table like this. We have Sunshine, Drama and Peaceful type of baskets, and then we have the type of plant, impact, flowering and trailing. We have the profits for the different type of baskets, and we have the total for each type of plant. Now if we go back to the question, we were told in terms of impact we have 2, 4, 3. So let's just put that down. Sorry if I go back. In terms of Sunshine we have 2 impact, 4 flowering and 3 trailing. So we have 2, 4, 3. And if we take a look at Drama, we have 3 impact, 2 flowering and 4 trailing. So let's just add this in. We have 3, 2, 4. And if we take a look at Peaceful, we have 1 impact, 3 flowering and 2 trailing. So we have 1, 3, 2. And if we take a look at the profits, for each basket we have 12, 20 and 16. So let's just add that in. We have 12, 20 and 16. And if we take a look at the total, we have 80, 140 and 96 for impact, flowering and trailing respectively. And from this, hopefully you can recognize that we wish to maximize P equals 12x plus 20y plus 16z, and we wish to maximize this objective function subject to the following inequalities. Here we have 2x plus 3y plus z being less than or equal to 80. Also we have 4x plus 2y plus 3z being less than or equal to 140, and finally we have 3x plus 4y plus 2z being less than or equal to 96. Well, actually we've also got another set of inequalities. X, Y and Z must be greater or equal to 0. Now with these sort of equations, we can rearrange these equations. For our P function, we can rewrite that as P minus 12x minus 20y minus 16z equals 0. And if we introduce slack variables instead of having inequalities, here you'd find we have 2x plus 3y plus z plus r equals 80. Okay, so I'm assuming that you're familiar with why we replace this first line, the first inequality symbol, with plus r. And then we have 4x plus 2y plus 3z plus s equals 140. And here we have 3x plus 4y plus 2z plus another variable, say t, equals 96. Okay, so we've got our 4 inequalities. And then for part B, we have to state the further restriction that applies to the values of x, y and z in this context. Well, of course, the values of x, y and z must all be integers, and that hopefully should make sense. So the values for part B, the values must all be integers. Okay, now for part C, we've got this simplex algorithm which is used to solve this problem. After one iteration, we've got this over here, this table. And then later on in the question, we've got the table for a second iteration. And for part C, we have to state the variable that was increased in the first iteration, justifying our answer. Now, just as a bit of revision, I think it would be helpful if we work through the problem to arrive at this second iteration table. And I think we'll do that now. Right, so we've got these 4 equations over here. Let's add them into our initial table. So if we consider this p minus 12x minus 20y minus 16z equals 0, if we add that into our table over here, we have p minus 12 for x, minus 20 for y, and minus 16 for z. And then we've got no slack, so we have 0, 0, and 0 for r, s, and t. The value is 0 because we had p minus 12x minus 20y minus 16z equals 0, so the value is 0. And that's it for now. And if you take a look at these 3 equations over here, noticing we have r, s, and t as our slack variables. For the basic variables, we have r, s, and t. For the first equation, that was an inequality before, we had 2x plus 3y plus z plus r equals 80. And then we had 4x plus 2y plus 3z plus s equals 140. And then we had 3x plus 4y plus 2z plus t equals 96. And then we fill the rest over here with zeros. And I think at this point it would be helpful if we label our rows. We have row 1, row 2, and row 3, and row 4. Our next step would be to identify the pivot. Now, looking along this P row, the most negative entry we've got is this minus 20. And therefore, for theta over here, we divide the value by the corresponding values in this y column, because this is where the most negative value is. So we have 80 divided by 3, which is 26.6, etc. And then we have 140 divided by 2, that's 70. Then we have 96 divided by 4, that's 24. Okay, And the smallest number we have over here is the 24, and therefore the pivot is this 4 over here. And in terms of what that means, if we work out row 5, row 6, row 7 and row 8, first of all, to work out row 7, we divide row 3 by 4. So if we divide row 3 by 4 to work out row 7, 4 divided by 4, that's just 1. And therefore we have over here 3 divided by 4, that's 3/4. 2 divided by 4, that's a half. Obviously here we have zeros. And then 1 divided by 4, that's a quarter. 96 divided by 4, that's 24. And therefore, hopefully you can see that the basic variable entry has been changed to y instead of t. So that's because we are leaving the starting vertex where x and y equal, x and z equals x and y and z equal 0, and we're increasing y, so y is no longer equal to 0. Okay, so in terms of our answer to part B of the part C of the question, we have the following. We have variable y, which was entered the basic variable column, and so y was increased first. Okay, now in terms of working out row 5, 6 and 8, all we have to do over here is simply add and subtract multiples of row 7. So if we consider row 5 in relation to row 1, row 5 is equal to row 1 minus 3 lots of row 7. And the reason for that is because we want a 0 here. So the way we can get a 0 here is if we subtract, if we work out row 1, take away 3 lots of row 7, because 3 minus 3 lots of 1 is 0. And therefore, working out the rest, we have 2 minus 3 lots of row 7, you'd find that to be minus 1/4. And then here we have minus 1/2. And we can continue this. We'd end up with 1, 0, minus 3/4 and 8. And this is R. Okay, now in terms of row 6, in relation to row 2, row 6 can be worked out by row 2 minus 2 times by row 7. So working that out, row 2 over here minus 2 lots of row 7 here. Working that out, we have S over here. And working this out, we have 5 over 2, 0, 2, 0, 1, minus 1/2, and 92. And in terms of row 8 we can work out by adding 20 lots of row 7 to row 4, and that will get a 0 here. And working that out for P, we have 3, 0, minus 6, 0, 0, 5 and 480. Okay, so that's our first iteration done, and that is consistent with what we have over here. Now, in terms of part D, we have to determine how many plants in total are being used after only one iteration of the simplex algorithm. Well, originally, if you look over here, in terms of the plants we can have at most, we have 80 plus 140 and 96. Okay, so if we go back here, the number of plants we had originally, we have 80, 140 and 96. And then we subtract off any bit of slack we have. So if we take a look at our table after the first iteration, perhaps if we look at the original table, you'd notice that we still have slack for R and S, okay? And therefore we have to subtract off 82, we have to subtract off 8 and 92. Okay, so hopefully that makes sense. So we subtract off this bit of slack in 8 plus 92. So this over here is the slack after the first iteration, and therefore you'd find we have 216 plants. Now for part E, we have to explain why for a second iteration of the simplex algorithm, the 2 in the Z column is the pivot value. So I think they're referring to this 2 over here. Well, just as we did before, let's try to work out that pivot. The most negative value in the P row is -6, and therefore we can work out the values of theta by dividing the value by the values over here. So theta over here, 8 divided by -1/2, you'd find that to be -16. 92 divided by 2, that's 46. And 24 divided by 1/2, that's 48. Okay, and obviously the smallest number is the 46, and therefore the pivot this time is 2. Okay, so let's try to put that in some sort of words. So the next pivot must come from a column which has a negative Z value in the objective row, so the pivot must come from the column Z. So that's part E done. So now if we go back over here, I think at this point we can actually finish off our table, and the only reason I'm showing you how to do this is just for extra revision really. But now that we know that the pivot is over here, writing down the rows over here, row 9, row 10, row 11 and row 12, we can quite easily work these out. Of course, for row number 10, we divide the this row over here by 2, so this becomes a 1. So we have row 6 over 2, and if we work out row 6 over 2, we have 5 over 4, 0, 1, 0, 1/2, minus 1/4, sorry, 1/2, minus 1/4, and 46. And over here, because the pivot was in the Z column, that increases, So that enters the basic variable column. And I think there was actually a mistake in the this over here. This, in my opinion, should be Z instead. Okay. So with that, we can now work out row 9, row 11 and row 12. Row 9, if we take a look at that in relation to row 5, to get a 0 over here, we would have to add row 5 to a half of row 10. So row 9 is equal to row 5 plus a half row 10. And in terms of row 11, we want this to be a 0 over here. So row 11 in relation to row 7, that's equal to row 7 minus a half of row 10. And row 12, to get this 0, in relation to row 8, row 12 is equal to row 8 plus 6 row 10. And if we work these out, let's look at row 9 first of all. Row 9 here will still have an R, and row 5 plus a half of row 10, we end up with 3/8, 0, 0, 1, 1/4, minus 7 over 8, and 31. And then for this over here, we still have Y, and row 7 minus a half of row 10, you'd find here we have 1/8, 1, 0, 0, minus 1/4, 3/8, and 1. And in terms of the objective row, for P, we have 21 over 2, 0, 0, 0, 3, and 7 over 2, and 756. So this is the table after the second iteration, and that's consistent with what we have over here. Of course, remember we have a Z over here. So for part F of the question, we have to use algebra to explain why this table is optimal. We have the following reason. If you take a look at P, the objective function, we have 21 over 2x, and then we have 0y, 0z, and 0r. And then we have a bit of slack as well, we have 3s and 7 over 2t. And all this is equal to 756. So in terms of an equation, we've got this over here. We have P plus 21 over 2x plus 3s plus 7 over 2t equals 756. And therefore you'll see, if we increase x, s and t, you'd always find when increasing these variables, P will always decrease. So therefore, we have something which is optimum. Okay? And now for part G, we have to state the optimal number of each type of basket that should be made. Again, looking at this table over here, you'd find over here, if we refer back to what X, Y, and Z were, remember X, Y, and Z were sunshine, drama, and peaceful. Okay? And hopefully you should be able to recognize from this table over here, we still have some slack. Okay? And therefore, we can only make one drama basket, that's for Y, and 46 peaceful baskets, because over here X hasn't entered the basic variable column, so therefore we can't include that. So in terms of part G, you'd find we can make one drama basket and 46 peaceful baskets. And the reason for that is X hasn't entered the basic variable column. Okay. And now for part H, the manager of the garden is able to increase the number of impact plants available each day from 80 to 100, and she wants to know if this would increase her profit, and we have to use our final table over here to determine the effect of this increase. You should not carry out any further calculations. Okay, let's just think about this. If you think about it, remember the definition of slack. Slack is basically the amount between an actual quantity and the maximum possible value of that quantity. And you'll see R over here, which, if we go back to the question, we're looking at impact plants and R is associated with that plant. You'll see essentially we have a slack of 31, and so we want to increase by 20. Now slack obviously is the amount between the actual quantity and the maximum possible value of that quantity. So we've got essentially a space of 31, and you'll see that over here. Now increasing by 20, because we've got a space of essentially 31, increasing the number of impact plants by 20 would have no effect. So I've put that down into words over here. The slack variable R associated with this type of plant is currently at 31, and increasing the number of impact plants by a further 20 would have no effect, and I've given the definition of slack over here. Question number 6. We have over here a project is modelled by the activity network shown in figure 4. The activities are represented by the arcs. The number in brackets on each arc gives the time in days to complete that activity. Each activity requires one worker. The project is to be completed in the shortest possible time, and for part A, we have to calculate the early time and the late time for each event using diagram 1 in the answer book, which we've got over here. Well, let's assume we start at 0. Now, this over here requires a fair bit of work, so we'll try to do this in an easy to understand way. A takes 4 days to complete, so this early event time, which we're going to do first, that takes us up to 4. And if we take a look at B, that takes 5 days to complete. So let's just put a number 5 over here. Alternatively, if we're at 4 already and C takes 7, 4 plus 7, that's 11. We put the bigger of the two numbers, that's 11. Remember, we want the early event time, the earliest time in which this event over here can start. So hopefully that so far makes sense. Now let's consider this over here. D takes 9 days. 4 plus 9, you'd find that to be 13. And if we consider this over here, well, if we're at A, and then if we go via E takes 6 days, so 4 plus 6, that's 10. Alternatively, we're at 13 already, another 2 days, that takes us up to 15. We choose the bigger number, so that's 15. Okay, hopefully that makes sense so far. And now if we consider this element over here, well, there's a couple of things to bear in mind. We can go from 11 plus the 9 from J, that brings us up to 20. We have the 13 plus the 5 from H, that brings us up to 18. And we have 15 plus the 4 from I, that brings us up to 19. Of course, we want the biggest one. That would be 20. Okay? So we put down 20 over here. Right, let's just get rid of this. If we now consider this element over here, of course, 11 plus the 8 from G, that brings us up to 19. And if we consider this final one over here, well, before that, 19 plus the 2 from L, that brings us up to 21. Here there's a couple of options. We can add the 4 from M to 20, which brings us up to 24. Or we can add the 5 from K to the 19, that brings us up to 24. So 24 goes inside here. And therefore, you'd find right now all the forward passes have been completed. And now for the backward passes, well, just work backwards. So here we have 24. And also for this dummy one, that takes us up to 24. Now 24 take away 2, that's 22. And we have 24 take away 5, that brings us up to 19. We want the smaller one this time, that's 19. Okay, hopefully that makes sense. And 24 take away 4, that's 20. Now 20 take away the 4 from I, that takes us up to 16. And there's nothing else which goes back to there, so we have 16 which goes here. Okay, now if we consider this over here, we have 20 take away the 5 from H, that brings us up to 15. And we also have 16 take away 2, that brings us back down to 18. We choose the smaller one. Sorry, am I missing something? 16 take away 2, that's 14 rather. So we have 14 over here, the smaller one. Okay, let's see what else we can do. If we consider this over here, we have 19 take away 8, which is 11, or we have 20 take away 9, which is also 11. So 11 goes here. Let's see what else we have. If we consider this element here, we have 16 take away the 6 from 8, that brings us up to 10. We also have 14 take away 9, which is 5. We also have 11 take away 7, which is 4. 4 is the smallest one, so 4 goes inside. And now 4 take away 4, that's 0. 11 take away 5, that's 6. Of course here we just have 0, the smaller one. So you'll now notice all of our passes have been completed, and we can now find out the critical path. We can start here and we can go to A, which brings us over here, and then we can go back here, down here, okay, and Then we can go via J, and then we go back down M, like here. And another way we can approach this is, once we're here, we can go back down here, across here, and then across K. So you'd find that there's two critical paths. Okay? So that's all we have to do for that, and I think at this point it will be a good idea to add on the float times as well, and I'll do that in a different colour. If we consider this b over here, well, b takes 5, so that takes us up to 5, and then we need to go to 11, so that brings us up to 6. Okay? So we have 6 over here. If we now consider e, we're at 4. 4 plus 6, that's 10. We want to end up at 16, the late event time, so we have a slack of 6. Okay, and what else do we have? We have this d over here. Well, 4 plus 9, you'd find that to be 13. We have this extra 1 as slack. If we consider this f, we're at 13 plus 2, that's 15. We want to end up at 16 for the late time, so we have a slack of 1. Over here as well for I, we're at 15. That takes 4. That brings us up to 19. We want to end up at 20, so we have a slack of 1. If we consider this h, we're at 13 plus 5, that's 18. We want to end up at 20, we have a slack of 2. What else do we have? We have L as well. We're at 19 plus 2, that brings us up to 21. We want to reach to 24, so we have a slack of 3. Okay, so yeah, that's basically it. So now for part B, on grid 1 in the answer book, we have to complete the cascade Gantt chart for this project. Well, I think it will be a good idea if we first of all add our critical activities. So we first of all add on this activity A, which is critical, the bit in orange. So we have A, which has a duration of 4. So let's just add this in. So this over here is what we have for A, and then after A we go via C. C has a duration of 7, so that takes us to 11. So 11 is over here. So that's C. And after C, well, if we continue with this one, we have J, which takes us up to 20. So 20 is over here. Let's just add this in. So this is J, and then we end up at 24, and that's M. So let's just add this in. We have M over here. Okay, and the other critical activity we have is over here. At 11 we go via G, so that's 8, and that brings us up to 19. So we'll add that in over here, and this over here is G. Okay, and then of course we finish off at 24, and this is K. So what you'll find over here is we have our two critical activities. Perhaps if we mention that here we have critical activities. And now we've got the other ones. Now, if we consider B has a length of 5. So let's just add that in. So B, that takes us up to 5. 5 is over here. And we add that in. And then you'd also find with B, we have slack as well of 6. So let's just add that slack of 6 in, which brings us up to 11. Okay? So this over here is the bit of slack we've got as well. Okay. And we've also got D as well, somewhere here. Now D starts when A is finished. So D has a length of 9. And 4 plus 9, that's 13. So D starts here somewhere. Actually, oh, we've got enough space. So I'll just clean that up a bit. So D, that starts at after A, and that has a duration of 9. So D starts at A. Sorry, it starts after A is complete. And then it has a duration of 9, which takes us up to 13. Okay, so 13 is over here. So this over here is activity D. Okay? And then you'd find with D, if we go back, we have a slack of 1. Sorry, we have a float of 1 rather. I don't know why I'm saying slack, but we'll add that in over here. So this is activity D. And then we have E as well. So if we go back to E, that starts after A is complete. And that has a duration of 6. So if we consider E, E starts when A is complete. And then that has a duration of 6. So 1, 2, 3, 4, 5, 6. That's over here somewhere. So this over here is E. And then we have 6 left over. So we have 1, 2, 3, 4, 5, 6 as left over here. So that's that. Okay. So after E, we have F over here. F starts when D is finished. D finishes earliest at 13. So 13 is over here, and this is when F starts. Okay, F starts here, and that has a duration of, if I go back, that has a duration of 2. So let's just add that on. So we have a duration of 2. This is F, and that has how many left over? That has 1 left over. So let's just add that in over here. So this is F. So after F is G, but G's already done. What else is there? A, F, G, H. So if we go back, H, that's over here. That starts when D finishes as well. So we have over here H, which starts here, and H has a duration of 5. Okay, so that takes us up to 18. So that has a duration of 5. So we have 1, 2, 3, 4, 5. Okay, so this over here is H. And in terms of what's left over is 2. So let's just add that in. We have 2 left over, as shown here. Now, so after H, I, so if we consider I, wherever that is, that's when F finishes. So when F finishes, we start I. So F H I starts here somewhere, and then that has a duration of, if I go back, 4. So we go 4 across. So 1, 2, 3, 4. That brings us up to here somewhere. So this is I. And in terms of the float was 1. So let's just add that in here. So this is I. And then we have J and K, which are critical, and then we have L. So L has a duration of 2. That's when we're at 19. So 19 is over here somewhere. So L, that has a duration of 2. So if we add that in, this over here is L, and then we have the extra float taking us up to 24. So that's over here. Okay, just tidy this up, and what I'll do now is I'll quickly shade in everything. So there's your Gantt chart completed. Okay, that's as neat as I can get it. Now, part C, we have to draw a resource histogram to show the number of workers required each day when each activity begins at its earliest time. I think this is actually a fair bit of work, so I think using different colours will actually help in this situation. So I think what we'll do over here is we'll label the colours. So we'll start off with A, and then we'll go C, and then we'll go J, and then we'll go M. Okay, so let's just add those in. So we start over here with A. If we go back, A has duration 4. So we have A, which takes us up to here. And then after A, we have C, which takes us up to 11. So let's just rule this off. We have C, which takes us up to 11. Okay. So let's just add this in. This is C. After C, we have J. J takes us up to 20. So let's just add J's here. So if we add that over here, this is J. Again, our critical activity. And then we finally have M, which takes us up to 24. So let's just add this in here. So this over here is M. And then we also have over here, I recommend adding this K in over here as well. Okay. So K starts at 19. So let's go back here. K starts at 19. So we have K's over here. Alright. And let's just add the other bit in. And we also have G as well. So let's add this in a different colour. We have G over here. And G, that starts at 11. So we have G's all over here. Okay, let's just rub that off like so. Now in terms of what else we have, if we find a different colour, we have B over here. Now B starts at 0 and has a duration of 5. So we have B's over here. And it's quite important that you add that in. Let's just roll off. And I'd say the next bit is actually quite hard to understand and get your head round. Let's just find a different colour for this. Let's choose this one. We have over here D. Okay. Now for D, D starts when B finishes, whenever that is. Okay. And hopefully that makes sense. Sorry, D starts when A finishes. Okay, that makes sense. So if we go back here, D starts here. And D has a duration of, if we go back, D has a duration of 9. So one of them days is taken up, so we have day 2, day 3, day 4, day 5, day 6, day 7, day 8 and day 9. So far we see that we require 2 workers, we require 3 workers so far. So that's D. And if we now consider E, if we go back, E starts when A finishes. So just select a different colour. E starts over here when A finishes. So here we have E. So E starts when A finishes. So E starts here. And E has a duration of, if we go back, of 6. So we have one of those days complete, then we have the other 5. Alright, so that's E done. Let's just rule that off. And now let's consider activity F. Okay, let's just grab a different colour. If we consider activity F, that starts when D finishes at 13 and that has a duration of 2. And D finishes here, so F goes over here. And that has a duration of 2. So let's just add that in to the diagram. So that's F. Now we've already done G. Let's now consider activity H. H, if we take a look at what that is, that starts when D finishes. Let's grab a different colour. So when D finishes at 13, that's when activity H starts. So H starts here. And H has a duration of, if we go back, H has a duration of 5. One of those days is complete, so we have H, 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 and H. Alright? So this right here is activity H complete. And then we have activity I. Activity I is complete when we have 15. So let's just grab a different color. So activity I starts at 15. So if we go back here, I starts here, and I has a duration of 4. So we have I, and then this I over here. Okay, so that's activity I. So we have H, I, J, K, and then we have L left over, and L, that starts at 19 once G is complete. So that has a duration of 2. So we have L over here, which starts here. Okay. So this is, if we go back here, that's L. Let's just add these different colors in over here as well. So we have L over here, and I'll just add the rest in quickly. Now for part E, the supervisor of the project states that only 3 workers are required to complete the project in the minimum time, and we have to use grid 2 to determine if the project can be completed in the minimum time by only 3 workers. Give reasons for your answer. So let's go back here. Now we only have 3 workers, okay, available. So 3 workers, if we just rule this off, here we have our 3 workers. As our restriction. Now we're asking in this question, can we complete the activities if we have 3 workers? Now if we consider this activity E over here, well, first of all, we have to get A and B done. That's quite important. Okay? And we need to get at least, well, it's a better way of phrasing it. Because A and C are critical, essentially, if we consider activity A, we have to if I think of the best way to phrase this, until day 4, only A and B can happen. So let's just write that down. Until day 4, only A and B can happen. That's the first thing. The next thing to pay attention to is that essentially we can move E forward, okay, and hopefully that makes sense. So let's just write that down. So this activity E, we can move forward by 1 day. So we can move E forward by 1 day. And so am I missing something here? E, sorry, before had, sorry, E had a duration of 6 rather. That was E. E finishes here. That was my mistake. So yeah, we can move E forward by 1 day, but the other problem is we have 3 days left over to use, and those are these 3 over here. So we have 3 days, let's write this down in black. We have 3 days left to use, okay, which will take us up to 24, and that's these 3 days, okay. So that corresponds to this over here. But the other problem is, if we consider this over here, let's just grab a different color highlighter, we have essentially 5 days to spare. So the rest of the activities, so that's referring to the H and the I, so that's referring to the sum of H and I, so sum of H and sum of I. This over here requires 5 days. And we saw that shaded in grey in the Gantt chart, okay? And therefore you'd find that we need more days than 24 days. So let's just write that down. In conclusion, we need more than 24 days. And therefore it cannot complete it, so therefore it cannot be completed by day 24 by 3 workers. So therefore, for us to complete this project within 24 days, we need 4 workers. Okay. So that resource leveling question, in my opinion, is quite difficult to understand, but hopefully you should be able to recognize what I've said over there. Okay. Question 7. A linear programming problem in X, Y, and Z is described as follows. We have to maximize P equals 3x plus 2y plus 2z. Subject to these conditions, 2x plus 2y plus z is less than or equal to 25. X plus 4y is less than or equal to 15. And x is greater than 3. Now for part A, we have to explain why the simplex algorithm cannot be used to solve this linear programming problem. It's quite a straightforward answer, in that the simplex algorithm can only work with less than or equals to constraints. And here we've got a greater or equals to constraint. For part B, the big M method is used to solve this linear programming problem. We have to define in this context what M represents. You must use correct mathematical language in your answer. Well, quite a straightforward answer. M is an arbitrary large number, and I always suggest letting M equaling something like 1,000,000. Perhaps if we write that down, that's the answer we have. Now for part C, we have to, well, for part C, the initial table for a big M solution to the problem is shown below, over here, and we have to explain clearly how the equation represented in the basic variable T1 row was derived. So that's this over here. Well, I think this requires a bit more work than then it's worth. I think for this sort of problem, I think it will be a good idea to first of all write down our inequalities. So we have to maximize this equation subject to these inequalities, and where we have this x being greater or equal to 3, we can rewrite this as, well, let's consider each of these in turn. If we consider this first inequality, 2x plus 2y plus z is less than or equal to 25, we can rewrite that as 2x plus 2y plus z plus s1 equals 25. For this next one, we have x plus 4y plus s2 equals 15. And now for this x being greater or equal to 3, we have to be a bit more careful. We have to include a surplus variable and an artificial variable. Okay, and the whole idea with this big M method is to drive the artificial variables towards 0. So where we have x being greater or equal to 3, we can rewrite this as x minus s3 plus t1 equals 3. Okay, let's perhaps write this out all in line with everything else. We have x minus s3 plus t1 equals 3. Okay, and if we rearrange this equation in terms of our artificial variable, hopefully you can see t1 is equal to 3 minus x plus s3. Okay, and well, that's all we have to do for part C. However, for part D, if we have a look at part D, we have to show how the equation represented in the basic variable row P has been derived. So we're looking at this slide over here. And well, I think it's quite straightforward how to arrive at that conclusion. First of all, from here, we can rearrange this P to say that P equals 3x plus 2y plus 2z minus m lots of t1. Okay, and if we call this equation 1 and this equation 2, we will essentially substitute in equation 2 into equation 1. So if we sub equation 2 into equation 1, you'd find over here we have P equals 3x plus 2y plus 2z minus m lots of this bit in green over here, which is 3 minus x plus s3. Okay, and if we tidy all this up a little, we have 3x plus 2y plus 2z minus 3m plus mx minus m s3. Okay, and if we rearrange a bit more, we have P equals 3 plus m lots of x minus 2y minus 2z plus m lots of s3 equals minus 3m, and therefore you'd find P equals, you'd find we have P minus minus ms3 let me just make sure I'm doing everything right. Sorry, I was supposed to put over here minus 3m. Okay, and that's over here. Now, we can therefore conclude that we have p minus 3 plus m, lots of x, minus 2y minus 2z plus ms3 equals minus 3m. And essentially, we put this into what we have over here. That's consistent with this initial table. Okay. And now for part E, the table obtained from the first iteration of the big M method is shown below. So they've used the big M method over here to obtain this table over here. And for part E, we have to solve the linear programming problem starting from this second table. You must give a detailed explanation of your method by clearly stating the row operations you use and state the solution by deducing the final values of p, x, y and z. Well, if we take a look at our initial table, the most negative value we have is over here, and therefore our pivot value will lie somewhere in this column. And the way we can work that out, if we work out values of theta, well, first of all, let's label this row 1, row 2, row 3 and row 4. We can work out a value of theta by dividing the value by the corresponding values in this column here. 25 divided by 2, that's 12.5. 15 divided by 1, that's 15. 3 divided by 1, that's 3. Okay, and therefore you'd find over here the pivot to be 1. And because the pivot's 1, essentially we replace this t1 with x, and that's exactly what we have over here. Okay, and then to obtain these values, we add and subtract multiples of the other data. So perhaps if I add these into this table here, let's just make sure I'm consistent, right? Essentially this minus 3 minus m, that's the same as minus 3 minus m. Alright, hopefully you can recognize that minus 3 minus m is the same as minus lots of 3 plus m. Now essentially, as we were doing here, we want this element to be 0. So row A is equal to row 4, okay, row 4 over here, plus 3 plus m, lots of row 7. So we have row A equals row 4 plus 3 plus m, lots of row 7. And then hopefully you could recognize, if we write that down, row 8 equals row 4 plus 3 plus m, lots of row 7. If we actually write down what row 8 is, you'd find over here, obviously row 7 is the same as row 3. So perhaps if we also clarify that, row 7 is the same as row 3. So of course here we'd just have p. Here we'd have 0. And then here we'd have minus 2 plus 3 plus m lots of 0. and the same thing happens here. And then here we have to be a bit careful. We have m plus 3 plus m times by minus 1, which is minus 3. And then here we have 0 plus 3 plus m lots of 1, which is 3 plus m. And then here we have minus 3m plus 3 lots of 3 plus m, which is 9. And that's exactly what we obtain over here. So just be a bit careful. But the only reason I wanted to show how we obtain these values is just for the sake of clarity, really. Okay, so hopefully all that makes complete sense. So we have R4, and then we have R5 to R8. Okay, and if we just label these R5, just make sure, here we have R5, R6, R7 and R8. Now we need to work out the values of theta to then identify where our pivot goes. Now we have theta over here, which we can find out. Well, first of all, we look for the most negative entry. Now the minus 3m is the most negative. The minus 3 is the most negative. So theta, let's work out these values. We have 19 divided by 2, which is 9.5. So we have 19 over 2. Then we have 12 divided by 1, that's just 12. 3 divided by minus 1, that's minus 3. Of course, we want the smallest positive number. That corresponds to this over here. And therefore, you'd find this 2 to be our pivot. Okay? And therefore, our pivot corresponds to this S3 column. So this increases into the basic variable. So instead of us having S1, we'd have instead S3. So let's just write that down. We have here S3 instead of S1. And then the way we can work out this row number 9 is to divide row 5 by 2. So row 9 equals row 5 divided by 2. So we divide this row by 2, so we have 0 divided by 2, 2 divided by 2, 1 divided by 2, 1 divided by 2, 0 divided by 2, 2 divided by 2, minus 2 divided by 2, and 19 divided by 2. Okay, and then for row 10, row 11 and row 12, we would have to add and subtract multiples of our pivot row. Okay, of this row over here, of this row 9. So essentially we have a 2 over here, sorry, we have a 1 over here, and we want these remaining elements to be 0. So for row 10, in relation to row 6, we have row 6 minus row 9. Okay, hopefully that makes sense. So we subtract row 6 from this row over here. So we have 0 take away 0, which is 0, 4 take away 1, which is 3, 0 take away a half, which is minus a half, and then we continue this. So we have minus a half here, 1, 0, 0, and here we have 5 over 2. with row 11 in relation to row 7, we would have to add row 7 to row 9, because again we want a 0 here. So we have row 7 plus row 9. So we have row 7, 1, plus 0, that's just 1. And then we have 0 plus row 7 plus row 9. So we have 0 plus 1, which is 1. 0 plus a half, that's a half, and we continue this. So we have a half here, and then we have 0 here, 0 here, and 25 over 2. So this over here is S2, and here we still have the X. Okay. And finally for this P row, we can work that out in relation to row 8. We would have to add on 3 lots of row 9, and that will make this a 0. So we have 0 plus 3 lots of 0, which is 0, minus 2 lots of minus 2 plus 3 lots of 1, that's just 1, and we continue this. So we have minus 1/2, 3 over 2, 0, 0, and here we have to be a bit careful. We have row 8, that's 3 plus m, and then we add on 3 lots of minus 1, so we have 3 plus m minus 3, that's just m. And then here we have 9 plus 3 lots of 19 over 2, which is 75 over 2. Okay, and again we have to perform another iteration, working out the values of R13, R14, R15 and R16 can be done by first of all working out these values of theta. We have to identify the most negative entry in the objective row. That would correspond to this minus 1/2. So we divide these values by the entries in the Z column. So we have 19 over 2 divided by 1/2, that's 19. 5 over 2 divided by minus 1/2, that's minus 5. 25 over 2 divided by 1/2, that's just 25. And you'd find the smallest value, the smallest positive value, you'd find that to be 19. And therefore, this 1/2 is our pivot row, so our pivot value. And instead of us having an S3, we replace that with Z. So we have Z, S2 and X, and finally P. Now, to work out row 13, we would have to divide row 9 by 1/2, and that's the same as multiplying by 2. So we have 2 lots of row 9. So 2 lots of row 9, we have the following values. We have 0, 2, 1, 2, 0, 1, 2, 0, 2, minus 2, and 19. Hopefully all that makes sense. In terms of row 14, in relation to row number 13, well, row 14, that's row 10, and then here we would have to add on a half of row 13 to get this to be 0. So for the S2 row, we have 0, 4, 0, 0, 1, 1, minus 1, and 12. x over here, for row 15, we have row 11. Remember, we want a 0 over here, so we have row 11 minus a half of row 13. So working out the x row, we have 1, 0, 0, 0, and 0. And here we have minus 1, 1, and 3. And finally, for row 16, we have row 12. And then we have to add on, remember we want this to be a 0, so we have to add on 1/2 of row 13. So working out this over here, we have 0, 2, 0, 2, 0, 1, and here we have 47. Now here we have to be a bit careful. We have m plus a half lots of minus 2, which is m minus 1. Okay, and now you'd find, if we delete the last page, now you'd find that we have over here all the values in the objective row which are now positive. Alright, so we have an optimal solution. So let's just write that down. We see that all the values in the objective row are now positive, and so the solution is optimal. Okay, and therefore if we work out the value of p is 47. If we work out the value of x is 3. We have no y value in the basic variable column, so y is equal to 0. And z is equal to 19. Okay, so that concludes the end of this paper. I hope you found it helpful. Don't forget to like, share and subscribe, and hopefully I will see you all on the next video.